In this video, we are going to solve a linear differential equation. In fact, to be more precise, a linear initial value problem using Laplace transforms. The equation in question is the following. 2 times the derivative of y plus y equals 0 with initial value condition y of 0 equals -3. The y here is a function of some variable. Let's say it's a function of variable t. We are looking for the function y such that this equality will hold, and along with that, y of 0 will be equal to -3. By the theory of linear equations, we know that there must be exactly one such function. And now the method of Laplace transforms allows us to find that function in the following way. So the first step, the first thing we want to do is to transform the two sides of the equation by Laplace. So we apply Laplace to both sides of the equation. On the left-hand side, we'll have Laplace of 2y prime plus y, and on the right-hand side, we'll have Laplace of 0. We're not going to, at this point, do anything with the initial value condition. The left-hand side of this equality can be simplified so as the right-hand side. For the left-hand side, we can use linearity of the Laplace transform, and then we get 2 times Laplace transform of y prime plus Laplace transform of y. What about the right-hand side? What do we get on the right-hand side? Well, again by linearity, or by applying the definition of Laplace transform directly, we can see that Laplace transform of the function constantly equal to 0 is the 0 function. So Laplace transform of 0 is 0. Why did I say that we can get it by linearity as well? Well, you can think of it like this. Laplace transform of 0 equals Laplace transform of 0 times some function, maybe the constant function 1, and then the 0 goes out as a consequence of linearity, we get this. So whatever Laplace transform of 1 is, this evaluates to 0 times that, which is always 0, of course. Another way of thinking about this is to present 0 as a linear combination, but an empty linear combination, which always evaluates to 0. And then Laplace transform of the linear combination must be equal to the linear combination of transforms. In both cases, we have empty combination. So in the first case, we have the 0 inside the transform. In the second case, we have the 0 as the final expression. Great. Let's come back to the calculations we were performing here. So Laplace transform of 0 is 0. We can get it by theoretical reasons or just directly by applying the definition of Laplace transform. And on the other hand, on the left-hand side, again, by linearity, we have this expression. And now we want to continue with the calculation. And in order to do that, we will have to invoke the formula for the derivative of Laplace for the Laplace transform of the derivative of a function. And according to the formula that can be derived by the definition of Laplace transform, when a function is suitably nice, and that what that means should be extracted from the theory, then the derivative will have Laplace transform that's equal to the following. I'm just trying to make sure that I will not get the formula wrong. Okay, there we go. So it's S multiplied by Laplace transform of y minus y evaluated at 0. And you see this is here, it is here where the initial value condition will start to come into the play. Okay, so we get that Laplace transform of y prime is equal to S times Laplace transform of y minus, and y of 0 was given to be minus 3, so it's minus 3, so that's plus 3 then. So we get S times Laplace transform of y plus 3. Now what we want to do is to put this back into the equality. Which equality am I referring to? This one. So in here, I want to put whatever L of y prime is. And L of y prime is this. So then we'll have 2 times S times L of y plus 2 times 3 plus L of y equals to 0. Let us pause here a little bit and say a few words of where are we heading to. So if I go all the way back to the equation, there we go. I had an equation where the unknown was a function y. So what I'm trying to achieve now is to get an equation where the unknown will be Laplace transform of y. If I know what Laplace transform of y is, then I can recover back what y is through the inverse transform. So we are aiming at getting an equation with Laplace transform of y being the unknown. And so then at this point, in this equality, what we want to do is to group L of y's together so that eventually we can solve the equation and express L of y as some expression of s. Okay, so then proceeding with that, 2s plus 1 times L of y must be equal to minus 6. So then L of y must be equal to minus 6 divided by 2s plus 1. And now the question is, what is y? In these few steps from here to there, we not only wrote down the equation with L of y being unknown, but we also solved it. Usually, with other examples of similar type, this process will be quite simple. The more complicated process is, from this point on, after I know what is L of y, to determine y, when I have to do the inverse transform of the rational function I get here. For that, in more difficult examples, I would have to use the partial fraction decomposition and linearity of the inverse transform. In this case, however, I can avoid that because I already have an expression that I can recognize to be coming from a formula. When with more difficult rational functions we want to use partial fraction decomposition, there we are aiming to get a linear combination of expressions recognized from formulas, but this one is already one, so we don't have to worry about partial fraction decomposition anymore. Let us see how can I recognize which formula to use here. So for that, let's recall what the formulas are that we have. We have a formula saying that Laplace transform of t to the power n, sometimes the formula can be with a variable t or with a variable x. it does not matter what variable we use. What matters is the meaning that the formula has. So that's the formula for t to the power n. Then we have a formula for e to the power a times t. The formula is this. Then we also have some formulas for L of sine of kt. The formula is k over s squared plus k squared. And then there is also a formula with a cosine. Now, among these formulas, which one would match with the fraction we have here? Does this fraction match with this expression? It does not, because in this expression the denominator is some power of s, whereas here the denominator is not a power of s. There is also plus 1 here. Does it match with this? No, because in here, in the denominator, s appears s squared. Does it match with this one? And at first glance, you might think that it doesn't match here either, because here we have no coefficient in front of s. So what we want to do is to try our best to still make the match. And the best bet we can make for achieving a match is with this one, where we will try to get rid of the coefficient in front of s. So let's see how this can be achieved. The thing is that with the magic of mathematical manipulations, we can rewrite the fraction as follows. What I can do here is to take out 2 from the entire expression. So I'll have 2 times s plus a half. And then I divide 6 by 2. I will be left with minus 3 divided by s plus a half. And now we have something which is very similar to the thing coming from the formula, where we just need to note that a needs to be minus a half. So with a being minus a half, we seem to get the match. However, there is still a little obstacle, minus 3. What do we do with that? Now the thing is that because of linearity, we can separate minus 3 from this fraction. So we can write this as minus 3 times 1 over s plus a half. So what we get is that L of y is equal to this. That would make y equals the inverse transform of minus 3 times 1 over s plus a half. And as I said, by linearity, we can take minus 3 out. So we'll have minus 3 times inverse transform of 1 over s plus a half. Okay, now we are very close. What is inverse transform of 1 over s plus a half? This is the matching we were talking about. So if I want to have 1 over s plus a half on this side, then on the other side, for the formula we had earlier, maybe I scroll back up here to show you the formula. So I'm talking about this formula here. If I want to have on the right hand side that, on the left hand side I need to have L of e to the power minus a half t. I just want to double check that we are indeed working with the variable t here. Yes, we are. We said y is a function of t. Wonderful. Okay, so let's go back here. So since L of that exponential function is equal to that fraction, then the inverse transform of that fraction will be the exponential function. So we get that this thing is equal to minus 3 times e to the power minus a half times t. And that's the y we were looking for. Let us now double check that the answer we got is indeed right. How do we do that? Well, first of all, let's remember the answer we got. It's this one, that y is equal to minus 3 times e to the power minus a half times t. And then we go back to the equation. We want to copy this equation down to the place where we got the answer so that they're together. And what we want to do after that is to make sure that the y we got indeed satisfies the equation. Remember, by the theory of linear equations, this equation, and to be more precise, the initial value problem, will have a unique solution. So if one thing is a solution, that must be that unique solution. Okay? With y being equal to that, do we have equality, the first one as well as the second one? So let's see. What will be 2 times y prime? Well, y prime will be minus 3 times minus a half by the chain rule times e to the power minus a half t. And the y is minus 3 times e to the power minus a half t. So that thing is equal to, must be equal to, and that's what we want to check, whether it's equal to or not, 0. Let's see what happens here. The 2 minuses become a plus. The 2 cancels with that 2 there. And then indeed, the two things together give 0. Because one is the same thing with a plus sign and the other is the same thing with a minus sign. What about the initial value condition? We shouldn't forget about that. Does the initial value condition hold as well? Well, if I put t equals 0 in this equality for y, let's actually carry out that calculation. So y of 0 must be, well, will be equal to minus 3 times e to the power minus a half times 0. And e to the power 0 is 1, of course, so the answer is indeed minus 3. So the initial value condition also holds. So quite remarkably, we didn't make any mistakes. And now we can be happy that we solved an initial value problem using the method of Laplace transform.